opportunity to give the tutorial today. So as Rashid mentioned, today we are going to go through a little tutorial on how to use convolutional neural networks for retina classification. So my name, as Rashid mentioned, is Hernán. So I work in Ecuador. So I'm a researcher. I started not so long ago in Ecuador, coming back from Germany. And I have about like, I don't know, 10, 12 years doing bioimage analysis, especially focused on understanding tissues. So let me show you the screen so that we can start with the tutorial. 1 second, please. Yeah. Okay, there you go. So I hope everything is visible. Yeah, I think it's visible from the computer. Yeah, so you can see my screen. I hope you can hear me. If there is a problem with the audio, please let me know.
Yeah, we can hear you well.
Perfect. So as I said, today the tutorial will be about retina classification using convolutional neural networks. So in this tutorial, the idea is to give you a basic guide through how to use deep learning for medical image classification, and we will focus on a specific problem that is the diabetic retinopathy. In a particular case, when we use retina fundus images, this is a very well-established method to study this disease. Yeah, so we'll use a real-world data set, and we'll try to implement convolutional neural networks from scratch. And also we'll try to we'll use pre-trained models, and we'll try to make a comparison to see how they perform in this specific data set. And this also will include that we have to do some pre-processing of the data, and we will do evaluation performance. And finally, we will end up trying to use to interpret a bit more the results you see in the class activation maps. Yeah. So the tutorial is designed to work in Google Colab with GPU support, and is also tested in Linux and in Windows, but with GPU acceleration. Yeah. So today I will run it in my local computer in Windows. So you will see how it works in Windows, but I will have a little space to show a small change that you have to do in Google Colab so that you can run it also there. Yeah. So what is the basic idea? So we'll have an input that are images of retina, and we'll have an Excel file with the annotation of the images, meaning what is indicating the retinopathy grade. And the output will be first the training models and also interpretable performance of the models. Yeah. So let's start. So we'll start with a very brief introduction. So as you know, deep learning nowadays have become one of the most powerful tools to study images, and this is also the case for medical image analysis. Why is this? Because it enables the automatic detection of complex patterns with a very high accuracy. So, and also, if it is properly used, reduce this is particularly used to analyze retina fundus images that are basically photographs of the back of the eye, which can capture actually subtle changes in the texture and structure of the retina that may indicate the presence of different diseases. In this case, as I said, we'll focus on diabetic retinopathy. Yeah, diabetic retinopathy is one of the leading causes of blindness worldwide, especially in working age adults. And the early diagnosis through retina experience is essential to reduce the problems with the disease. What is the problem? That, as you may expect, this is always time-consuming, resource-intensive, and depends a lot on the experience of the doctor that is checking this. So that is when the deep learning comes in place, and in general, the image processing and the image classification task. And the idea is to try to automate these processes in scalable solutions that will help to support clinicians to identify the disease stage, reducing the diagnosis times, and also help to understand a bit more the disease. You see, if we use interpretable models, as we will try to do here. Yeah. So let's see. Let's start then with the practical part. So In the notebook, you will see 4 sections. So the introduction that I just went through. So you have a sections with the prerequisites that I will go through now. That will be basically what you need to run the tutorial when you are doing locally. And then we have to the main part, and the hands-on implementation. We will go through step by step to all the processing steps that I mentioned you. And finally, we will have a discussion of the challenges and also the limitations of the tutorial, right? So let's start with the prerequisites. So as I said, so you have 2 options to do this. You can run it locally on your computer using either Windows or Linux. And when it was tested, it was not test for Mac. Or you can use Google Colab. Yeah. So first, I will show you how we can do it with the Windows computer. I suggest to use Conda. You can use the version Anaconda or Miniconda, the one that you prefer. And here you have brief introductions how to do it, how you can create your environment, basically with the commands. Make it a bit bigger. Yeah. So basically, you can create with the commands conda create, and I call my environment Retina classification with Python 3.10, and then we activate the conda environment. So with this, we can already start, and everything that we will do today we'll use PyTorch. Yeah, there are several libraries that one can use to work with deep learning in Python. So one of the most used nowadays is PyTorch because it's easy to use and it's very powerful. Yeah, so this is the one that I choose for the tutorial today, and this is the one that is implementing in the notebook. So if you want to install it in your computer, you have to install it. You can follow this this command line that is here. So you have to be sure that you have CUDA in your computer installed, and you have to check that the version of CUDA is compatible. Yeah. In this case, I am using CUDA 11.8. That's compatible with my computer and installed there. So this is the only point that you have to be careful when you are installing the PyTorch in your computer. Yeah, and we will use the Jupyter Lab to work with the notebooks. So this is also installed here. So these are the 2 pre-steps that we have to do. If you are working in Google Colab, it's much easier. You can skip this part, and I will show you how it looks in Google Colab. In Google Colab, you probably most of you have worked with it. You basically have to open Google Colab, log in your account with Google, and just upload the notebook. In this case, you don't have to install anything. Yeah, and the only thing that you have to check is that you have the session enabled with GPU. So for this, you go to runtime, you can go to change runtime type, and you make sure that you choose GPU. Yeah. So what we choose GPU because otherwise the calculations will take ages. Yeah. So with GPU enabled calculations, we can do this relatively fast. Perfect. So we have the 2 options, and from here on, there is only one small difference between running it locally than in Google Colab. If you run in Google Colab, you only have to run this. You have to remove everything and just keep this installation for the library. That is the PA tool. You have to remove everything else because everything else is already installed in Google Colab. So in order to avoid any problem with the compatibility in the libraries, don't install anything else, but only this one. That is the only one required in Google Colab. It will run locally. So here are all the libraries that you need to install. So as I said, so this is a fully stand-alone notebook, so you don't have to stand anything extra. If you run this part here, you can already start the calculations in your local computer. So you will see that, so in my case, since I already installed this in advance, so you see that all the packages are already installed. So you can run. So the basic packages that we will use for you to know. So probably many of you are familiar with NumPy, Pandas, Matplotlib to make some calculations. We will use OpenCV to do some processing in the images, same as Pillow and Skylearn. So we'll also use TensorBoard to visualize the results of the training. We will see this later. And OpenPySL to open the Excel file that we have as of for the data. Yeah. So you have something like this where all the packages are installed. So this is the first part. And with this, you can start either in local computer or Google Colab, as I said. And from here on, is exactly the same. So there is no difference between running locally or in the cloud with Colab, for example, with Colab. And so I will continue from here on only with the compilation for the local computer. And I will tell you about the dataset that we will use. See now? So the next point is first we will have a look at what we are going to actually analyze today. So we'll use a dataset of diabetic retinopathy, and we'll use an open dataset from the Mesidor dataset. So you have also in the notebook where you can download directly the whole dataset. So you have the link here. So you can open, you can go through the website. So it's a well-established dataset for this kind of problems. You have the full description of the dataset here, and you can download the full dataset there. Yeah. So what is what the dataset consists on? So we have 1,200 images of the eye retina. So from the posterior pole. So these were acquired from 3 ophthalmology departments using a video 3 CCD camera. So we have images from 3 labs. So this is also quite good because it gives a lot of variability and will be good for the models. And from these images, 800 were acquired with pupil dilation and 400 without. So this is also something interesting because the size of the retina is different in the data set. It's something that we have to somehow normalize for our algorithm to perform better. Yeah, something that we'll see when we are preparing the data set. So regarding to the medical diagnosis in this data set, so there is actually 2 diagnoses available from here. So the first one is the retinopathy grade. So, and it's the one that we are going to use here. So basically all images are classified in 4 classes, going from 0 to 3, where 0 means that the pupil is normal, and 3 is a high grade of retinopathy. And here are the parameters that the doctors use to do this annotation. Yeah, so we're not going through details. If you want, you can check more carefully. What is important for the tutorial today is that we will go from 0 to 3, where 0 is normal, 1 is a slight degree of retinopathy, and 3 is a very severe one. Yeah, so this is the data set that we analyze. But in this data set, you will also have information about the risk of macular edema. In this case, we have 3 classes. We have no risk, when you have moderate risk, and high risk. So meaning from 0 to 2. So the tutorial is also built that you can also adapt it to analyze this other classification class. I will show you how to do it when we are in that part. But today we'll focus in the first one for the tutorial. But it can be easily adapted. I will explain you how you can do it when you work with the notebook. Yeah. To finish this part, as I said, you can download the full dataset from the address that is there and using the correct reference of the work. And for this tutorial, in order to save a bit of time and also so that you can practice a bit more, so this dataset was already downloaded and was a bit pre-processed. So the pre-process was very simple. The images were only downsampled 4 times in each dimension. So the images are relatively big. However, for the models that we will use today, we don't need all this super high resolution. And to speed it up, the loading and the downloading, so that you can also do this practice today. So I already pre-processed the image. Basically, as I said, just downloading 4 times. So I still fit in the models. They keep all the information that we will need to use it for here for this specific purpose. And then you can also you can download it from the Google Drive dataset. So you can see it here. Yeah. Anyway, in the notebook, if this is not working, so if you have problems, I will check. But so it should be fine here, as you can see. I will have a look. But anyway, in the notebook, you will see we will download the images step by step. Yeah. So if you have problems there, please let me know. Yeah, I will have a look at the link for the full dataset later to see what is the problem. Maybe there is some issue with the rights for download. But don't worry about this. This was just if you want to do it for a different one, for a different task. But we will do it in the implementation automatically here. Yeah. So if you have problems there, please let me know. So let's start with the implementation itself. So let's go with the libraries that we need. So the first thing that we need to import are the libraries that we will use. So I try to put here all the libraries that we will use with a small comment so that you can go through them in case you want to check carefully, and also try to group them so that you see more or less what we will need. So I will go just very briefly here so that we have an idea. In the first block, the libraries just for handling operating system and also handling files. So here we'll also import the libraries that we need to download the data that we need, and so on. Yeah, then we have libraries for the numerical and data analysis, the NumPy, Pandas, and math. So also for some plots, libraries for image processing, as I said, we'll use Pillow and OpenCV mostly. Some libraries for the machine learning utilities. So here we will use mostly sklearn. So we have for model selection, some metrics that we will use. And finally, we will have the part for the deep learning. That is basically all the PyTorch libraries that we use to train the models. Everything is installed here. So you have to go here and we run it. So it will take a few seconds until everything is implemented. So, and thanks for the feedback, as Rashid said, for the file. I will check at the end, but don't worry, we will have also the download in the notebook automatically. Yeah. So when everything is implemented, when everything, all the libraries are imported, so we go to the next steps where we check if the GPU is available and the number of workers that we have. So this depends on your computer, or if you are using Google Colab, it's the same. So in this piece of code, so you can see a function that basically is open PyTorch and checking for the devices that we have available. So if we have available, it will print the name of the device. If not, it will tell you that you don't have a GPU available. If you don't have GPU available, so there are a few options, a few ways to solve it. So the most likely one, so if you are in Google Colab, you have to check that your session is enabling GPU. So this is relatively easy. If you are working with your computer, it probably means that the installation of PyTorch with CUDA support was not properly done. So you have to check that the compatibility of CUDA and PyTorch is proper in your computer. Yeah. So this is the main problem that you can have here. But this is a checkup to see if this works, if you have GPU available. So if you don't have it, the notebook will work, but it will take ages. So it's not really doable. Yeah. So please be sure that you have the GPU available. So in the last part, you also print how many workers do you have, meaning how many workers you can use in the computation for the tutorial. And we run a simple calculation test that's basically a matrix multiplication in GPU to see that everything works well. So if everything is fine, so you will get a print that the calculation is done. If not, it fails. Yeah. So let's run it. So we'll run this. And this, for example, now I have a problem here with the initialization of my on my GPU. Okay, so in this case, you see that the no GPU was found. So there is a problem with the GPU in my case. So I'm really sorry for this problem. I checked yesterday, everything was fine. But don't worry. So what we can use is go briefly to. I will just quickly move to Colab, where I'm sure that I have all the GPU available. I'm really sorry for the problem. So yesterday I checked and it was not was working properly. So there should be some small problem with my GPU. Yeah, but we will try to do in Colab so that we can go through the tutorial without the interruptions. So in Colab, we do here, and then here you see that is what the proper output that you should be able to see. So you have GPU available. It will tell you what GPU you have. So how many workers? In this case, 2 workers are assigned in your session. The device that you are using is CUDA, and the test for the calculation was successfully. Yeah. So with this, we are sure that we are going to work in GPU and that everything will go smoothly. Yeah. So next important part before we start any calculation, especially when we are debugging and then we were trying to test models, is to set up a reproducibility. As you may know, so the current deep learning models are not fully are stochastic, which means that every time that you train a model, you will get a slightly different result. So this comes from the fact that all the models are initialized with random weights. So you start randomly and then you start to look for the optimal solution, basically. So if you want to have a fully reproducible setup, you have to set the seed that you will use in your specific task. In this case, I wrote a function to set up the seed that we will use so that every time that you run this notebook, you will get exactly the same results. Yeah. So these are all the variables that you need to set. You need to set the seed for torch, for PyTorch, for NumPy. So we use random also we set. And then we ensure that all the results are deterministic. So the process is slower, yeah, on GPU, but the results will always be the same. So as I said, this is important when you are especially testing pipelines, yeah? So when you have a deployed algorithm, then you can remove this, you can make it faster. But in this case, we want to have a reproducibility setup so that every time that we run this will be exactly the same. So we can run this part, yeah? So we just set up a seed. So the usual standard seed that is used is 42. You can choose any number. Actually, it doesn't matter. So the results will be different, of course, depending on the number that you choose, but it will be reproducible every time that you use it. Yeah. So with this, we are ready to start. So we have set up everything, and then we'll start with downloading the data. Yeah. So in the first cell that we have here, so we are downloading the data. So for this part, the data was split in 3 small data sets. Why is this? Is this just to be imported automatically with from the notebook, and to avoid that you have any request to run the antivirus, because you know with Google, so this is uploading Google Drive. So if the file is too big, so you have a request for check for the antivirus and gets problematic. So this is basically the dataset was split in 3 parts, and the function here will do the following: we take any of these files, so we put in the right format. It will download every single file that we have. You have 3 rar files that are compressing the data. It will extract everything in a temporal folder, and then it will put everything in a single file in a single folder that is called images. I will run this where we're explaining, so we gain a bit of time, because this, depending on your internet connection, can take a couple of seconds. Yeah, it will create a folder that is called Retina dataset. So all the data will be moved here. So you have a folder that is called images, and all the images will be downloaded there. So you can see here, it's downloading already the first RAR file that is called images 0. Now it's going for the second. As I said, there are three files. So let's wait for a second, and then you have the third one. All the files are downloaded. So you should be able to see in the local file all the images, and you have the images here. Yeah. So this is downloaded. You have the folder Retina dataset, is the folder we are going to work on, and a folder with the images. We have the 1,200 images that we will use. So the next, we are going to download and save the annotations. The annotations, as I said, is an Excel file that is also in a drive. So this is relatively fast. So you will also see, if you refresh, you have a file that is called annotations.xls. So you see that everything went through. So if you go through the code, so we'll make the directory, we check that the directory exists, and here you have the code to download the file. So now we are ready to do so. And this becomes the part that you have to modify in your code. So we have to define where the data is going to be, where the annotations are going to be, and what is the health condition that we are going to use. So if you are using Google Colab, here you can check only, for example, copy path for the images, and then I will copy it here. So you have the path where the images are located, and the same you can do for the annotation. Yeah, so this depends on where you are working on your computer, so be sure that you change it properly. So you have the data directory, is the data where the images are located, and the annotation path is the path to the Excel file. So as I said, in this Excel file, you have two annotations for two diseases. So the first one is the retinopathy grade, and the second one is the risk of macular edema. So you can choose here which of the columns of the file we will use to analyze. Here is a comment for the second option if you want to use it for later, if you want to try. For the tutorial, we'll use the retinopathy grade. So we put it here. So be sure that you change this properly. It's very important so that everything runs smoothly. Yeah. So now, once this is done, so this is the part that you have to modify according to your computer. So we will upload the file, the Excel file, and we'll have a quick look. So in this code, you can see how we use pandas to load the Excel file. So then we select only the columns that we are going to use. We only use the image name and the health condition. So we just rename it to have image name and label, just for consistency for later on. And then we'll create a new column where we will save the path, the real path of the images. Here is very important. It depends on the path that you define in the previous step. So when we are reading the data, we'll always read from the path that you define there. Yeah. So we get the unique labels in this case, how many labels we'll have, and the class names according. So we'll call it from grade 0 to grade 1. So we're just giving some names for display for later on so that we can display and then match directly. So here we display the data frame. So here you see how it looks. So we have the image name. So this is the image from the original data set. We have the label, as I said, from 0 to 3, and we have the path to the image so that we can open directly. Yeah, and as expected, we have 1,200 rows and 3 columns. So we have the data set ready, the annotation data set is there. And now, so the first thing that we will analyze is we will try to see how much data we have for each class. Why is this important? because in some cases we can have data that is not balanced. Actually, in most of the real cases, when we are studying real world examples, so the data is not balanced. So, which means that we have to also deal with this properly when we are setting up our model. Yeah. So what we do here, so we do the counts of the class, we get the percentages to have an idea, and we will make a little histogram showing this. So this is the code, so you can check carefully. And basically that is what we have. So we have a number of images, and we have also the percentage of data assigned for each class. As you can see here, almost half of the data belongs to the class 0, that is the normal case. So for the grade 1, we have only around 13%, and for the other classes, we have 20% of the images, more or less. So what is the problem? So these are called unbalanced data, and it's something that we have to take in account when we are defining our data set. Because what happens if we don't take care of this, that our model have a lot of information about class 0 and then very little information, for example, about class 1 and moderate information of class 2 and 3. So if we don't correct for this, probably our model will be able to accurately classify the first case, the case 0, but probably will be not so good for class 1 and so on. And this is not something that we want for a classifier. We want something that could classify properly more or less all the classes. Yeah. So this is something important. So it's always important to check your data before and to check how much data you have for each class. So here we have this. And now let's have a first look at the image. So let's see how they actually look like. So this is a piece of code that basically will take 2 examples per image. So it's something that you can also play with. If you want to draw more examples, you can add here more examples. In this case, I am running for two random examples from the image, and for each one of the classes. Yeah. So here it will make a plot that will have the number of classes times 4. This is just the size. And we'll take randomly the images. It will extract the images. Here we'll take the path for the image that we wanted to have. We'll open the image. It will transform to an ampere array for the plotting. So we'll also have a little extra information here. We want to extract a bit of the metadata, so we also understand a bit how the images look like. So we'll extract what is the width, what is the height, how many channels we have, and what kind of data we have. See what kind of image we have. We will print this for the first image so that we have an idea, and then we will see some examples of the images. So we will plot it. So let's see, yeah. So we have the image metadata. So for 4 images, 1 image of each grade, as you see, you have the name of the image, you have the grade. In this case, grade 0 for the retinopathy grade. So this is the shape of the image, the size. So you see that the images have different size for different classes. So which means that they actually have different size in general for they come through because they are from different labs. So in every setup, the images are slightly different size. So it's something that we also have to consider. So you see that the size are variable. In all cases, we have 3 channels, meaning that it's an RGB image, and the image depth is 8 bits. So for all of them. So we have an idea of what kind of data we are working with. And here we have some examples. Yeah, so we have for each column examples with grade 0, grade 1, grade 2, and grade 3. As you might notice, especially if you are not familiar with these kind of images, distinguish between the 3 different grades is extremely difficult by eye. So this can be only done by people that have a very good training on looking at a specific characteristic of the images. And that's why it's so important to have this kind of algorithms, because this can help us to identify the difference between these images. So first thing that we see there. So we can also try to run, if we want to see more examples, you can modify this, and then you can see here will take a bit longer because it's plotting more data. Yeah. So you want to have a more examples, you can change this, and then you can visualize all of them. So there are several things that one should notice here, and that are important also for the later processing. So the first one is that, as you can see, the images are not square, they are rectangles. We can also see from the size of the images. So the width is bigger than the height. And as you can see here, it's basically black space, it's dark space, so it's empty image. So in general, when we are working, especially with pre-trained models, we need the square images. And this case in particular is very useful because we are talking about an object that is spherical. So you have basically a circle there, so that is symmetric. So we are actually, with these images, we have a lot of data that we will not use at all. So you see here that we have black space. So we have to somehow make the images square first so that they can enter to the algorithm, but also better try to remove this black space on the sides, because something that will not be useful for our classification algorithm, because it doesn't give any information and could actually indeed give some noise to the model. Yeah, so it's something that we have to check. The second thing that we can observe here is that also the intensity, there are a lot of variations in intensity, in contrast and brightness in the images. And it's something that will also be good to correct before we start running any algorithm, and will improve the performance. So here are exactly what the issues that we identified in this just pre-analysis of the data. So first, the classes are unbalanced what we mentioned before. And the second, that the images are rectangular, so there are a lot of information on the sides. So how we can deal with this? So for the unbalanced data, there are different approaches to solve this. Yeah. So one is so we can do data augmentation. So it means that we can apply random flips, rotations, intensity variations, or even elastic deformations only to the minority class to increase the number, or artificially increase the number of images. So another option is to oversampling. So in the case of the images, the classes that have less data, the minorities that are underrepresented, we can either computationally duplicate them, or we can generate the synthetic data to generate the extra data for the classes and then have some more or less balanced data. A third approach is called the class-aware sampling. So in this, what we do is actually we implement sampling strategies so that every time that we have a batch for our training, we try to take it in a way that is more or less balanced. Meaning, for example, you have a batch of 40, just to round the numbers. I know that we usually don't use this number, but since we have 4 classes and you take a batch of 40, ideally with this class that we're sampling, we should take 10 images of each class. Since everything is random, will not be exactly 10, but we want to have like more or less an even proportion, yeah? And this is a strategy that we will use in this tutorial. So we will implement a sampling strategy to be sure that we have in every batch a balanced data. Other option is to use loss reweighting, meaning in the actual loss function of the algorithm, we penalize for errors on the minority class more heavily than in the errors with the class that have a lot of data. Different strategies that you can try. So today we will use the class-aware sampling. For the second part, that is a bit more simple. So we will do the following. So we are going to crop the images. So we'll automatically identify what is the part of the region of interest, meaning where is the retina, the ROI, and we will crop the image, and then we will use padding and resizing to have to keep the aspect ratio. So we don't want to modify the aspect ratio of the image. So we'll crop So then to have a square, we use padding to have a perfect square, and then we can precise to the size of the model that we need. Yeah. So that is what we'll do. And with this, so we are sure that we don't introduce any artifacts. We're not preserving the aspect ratio, and then we remove all information that is not actually useful for our model. Yeah. So with this, we are done with this exploration of the data. Sorry. And we are ready to start with the data preparation. So one of the most important process parts of the process when we set up this kind of models is the preparation of the data. Probably a lot of you have heard about the trash in, trash out, right? If you give trash to your model, you will probably get trash. So if you don't give to the model good data, probably the results will not be good. Doesn't matter how advanced or how precise or how big is your model. If the data is not good, so the results probably will also not be so good. Yeah. So this is a very important step where you have to pay a lot of attention, and that's why it's very important to spend the time checking the data, checking if the data is in balance, checking if you have artifacts in the image that need to be removed maybe before. And try to correct for big differences, or try to normalize as much as possible the data, so that your models can also perform better. Yeah. So very important step, and that's why we're taking quite some time in this part, and we will do it for the image preparation. Yeah. So you saw that all the images have different sizes, and so we have to standardize to a single size that we will use for all the models, so we can also compare the different models in a fair way. So we choose a standard image size that is 2024 times 2024, which means that after doing all the processing, we will take the images and then resize to this size, and this will be the input for our networks. So we will use a batch size of 38. That is something that will fit in most of the computers with the GPUs that you have. So if you have a more powerful computer, you can increase the batch size. If the memory in your GPU is smaller and you have errors during the training about the memory of the GPU, this is the parameter to change. So you can go a bit lower. Let's say you can go 16 or 8 or even 4 if you need to reduce this so that it fits in the memory of your computer. So we are going to use models that are not super big. So this should fit, 32 should fit more or less all the standard data, the standard setups of GPUs. And we are running Google Colab. It should not be a problem. It should run without any issue like this. Yeah. If you have a more powerful computer and you want to change the number of workers that you are using, you can also change here. So now it's common in Google Colab because we'll take only one of the two workers since we have only two. So if you are running locally, you can adjust this number depending on the number that you got in the first step when we are checking the number of workers that we have. So next, so we are going to use some pre-trained models. So as you might know, for many of the convolutional neural networks that are set up or are used nowadays, so many of them, most of them, come also with pre-trained models, and these models were trained in a very famous data set that is called ImageNet, that many of you probably have heard of it. So the ImageNet is a natural image dataset. So it's a huge dataset where the models were pre-trained. And this dataset was normalized to go to the models. So if we want to use these models, we also have to normalize our data according to those parameters of ImageNet. What are the parameters of ImageNet? So these are the three. So this is the mean intensity in the three colors. As I was saying, we are working with RGB images, like three-color data, 3 channels. So the normalization is slightly different for each channel, and also the standard deviation is slightly different. So what is the idea of the normalization? That you subtract the mean, and then you divide by the standard deviation. So assuming that more or less the data is normally distributed, the intensity of the channels. So since we are using pre-trained models, so we will use this normalization and we will define it here. And to make a fair comparison, we will do this normalization for all the models, even for the models that we will train from scratch. Yeah, great. So now we have defined all the initial parameters. So we go to the next part, that is splitting the data in train, validation, and test. Yeah. So since this is a tutorial, so we'll do a very simplistic way of this, that is taking from the whole data set, we take 20% for the test set, and from the 80% of the remaining, we will take 20% for validation, meaning 60% total of the total data for validation. And this we will use for the trainings and for the validation. If you have the data, and a more proper way to do it is to take a fully independent test dataset. So if you want to practice a bit more and you want to make it more realistic, for example, this algorithm, what you can do is you can take the data from the two laboratories for the test and for the training, and the other one for the test. So this will help you to understand a bit more the generalization of the models that you train. Yeah, so now here we're doing a tutorial. It's more like a toy model. So we will split the full data set in training, test, and validation. Yeah, for this we use the function train and test split. So this is relatively easy. We have to give our database. So we take the size of the test. In this case, we take 20% for the test and the rest for the validation. And here, important, so we will use the flag stratify. So what does this flag stratify? This makes the data balanced. So meaning, if you have unbalanced data as we have here, so if we just do randomly between test and train, it could be that in the train you have more data for one specific class, and in the other one, in the test, is not the same. Yeah. So we wanted to be sure that the data is split evenly. So meaning that in the train, the test, and the data set have more or less the same proportion of data for each class. So for this, we use the function, the flag stratify, and we stratify according to the label. Yeah. So this, so the functions internally does it automatically. Yeah. So we split from the training, and then here we plot a summary. Yeah, as you can see here. So now we have the training, validation, and test dataset. You have the number of images per class. And you can see here also that the percentage per class are similar for the training, the validation, and the test. So you see more or less 45, 12, 20, 20. For all of them, that was also the original distribution of data. So this is like this because we use the stratify function. If you have unbalanced data, you always have to use this to be sure that the data is evenly split between the three datasets. Yeah, so now we have split the datasets. So we have a defined number of images for each of them. And now we are going to define the dataset class. So here I define a function, a class that's called Retina dataset. So this basically what it takes, it will take my data frame. So it will take the directory with the files, and also you want to do some transformations. Yeah. So I have a function here that is called bounding box. So this function bounding box, what actually does is what I was just discussing before. So it makes the conversion to the format for to use OpenCV. Then we'll use a thresholding, the OSU thresholding, that is the most standard one, that basically wants to just take the black space out. We'll find the minimum box that will fit in the data. Yeah, so this you do in this part here with the coordinates, with the bounding box. So then we'll crop the image. Then it will take the maximum size, and then it will do a padding. So meaning that we'll make a square, and then we'll put the image in the middle. Yeah. and we'll get back the original image. So with this, we crop the image, we have squares, and we have also a small pre-processing data, pre-processing function. So that will use a CLI, that is a local enhancement contrast. So basically, it takes the image data, it takes the mask that we have before, and will increase the contrast using this local contrast enhancement CLI. That's one of also a standard. It will do for every channel, and then we'll give you the image out. And then here we have the definition to get the item. So shortly, what it does, it takes the image name, the label, the path. They convert it to RGB, to the processing that I mentioned, bounding box, cropping, pre-processing. If we want to make some transformations, we make the transformation, and it returns the pair of the image and the label. So we run this, should do nothing because we are only defining the functions. And then I will talk you about what I mean with these transformations, yeah? So to have a limited data set, we have only, in total, 1,200 images. So this is a relatively small data set. So this is a relatively small data set for this kind for models, especially if the models are big. So how we deal with that, or how we can improve the performance of the algorithm without having to acquire more images. So we make what is called data augmentation, which is basically computationally increase the number of images by making some slide transformations in the data. Yeah, so this is a very standard, also a very standard procedure when we talk about image processing. But for medical images, we have to be a bit more careful. Yeah, so we cannot use any augmentations, but only the augmentations that are these transformations that are medically make sense, that are physiologically relevant. So here I put you some examples. For in the retina, we can do horizontal flips because this will help us to increase the retina symmetry. So retinas are mostly symmetric, so we can do flips lateral. And here I put you with a comment, which is usually standard. When you have horizontal flips, you usually have also vertical flips. But in this specific case, this doesn't make sense because this is not physiologically doable. So you cannot have a retina that is upside down. Yeah, so we have to be very careful with the kind of augmentations that we use. In this case, I put it here on purpose so that you see that this should not be used. Yeah. So we'll also we'll have some rotations. So we are tilting the image 20 degrees because this simulates a bit of the tilting of the camera. So we use a small degrees, so only 20, or a small value for the degrees, only 20 degrees. We will not use the full rotation, but because again, if we use full rotation, for example, 100 degrees means that the retina is 100 degrees up. So it's also not physiologically relevant. Yeah. So we have to make sure that all these augmentations that we use are relevant physiologically. Yeah. And that depends on the system that we're working on. In this case of the retina, we use small tilting, small variations, small rotations is fine, but we cannot use full rotations. Yeah. And we will also do some color jittering to simulate variation across different devices. So we change brightness, contrast, and saturation, but just a bit. That we use values of 0 to 20%, very small variations. Yeah. The problem is if you use too big variations, it could also introduce artifacts. So these are the transformations that we use. First, before doing any transformation, we have to resize to the size that we wanted to have, the one that we defined in the previous step. Then we transform to a tensor. That is the format that we'll use for training, and also it normalized from 0 to 1 the images. And here we have the normalization with for the pre-trained models using the data from the ImageNet. One important thing, these transformations have to be defined separately for the training and for validation and test sets. Why? Because all the transformations, all the data augmentations should be done only to the training, not to the validation or to the test sets. Yeah. So we give more data for the algorithm to learn more variability, but it has to perform properly in the original data. Yeah. So for the validation and test, we only do resizing, tensor, and normalization. So we don't do any data augmentation. Yeah. Something very important. So we have it here. So we run this, and then we go to the next part, that is how we can create a balanced data set. So as I said, there are several strategies. So we'll use a balanced sampler. So for this, we'll use a weighted random sampler. There's a function that's implemented in PyTorch. So what we do is we take the labels, we count how many labels we have in each class, and we assign a weight, and the weight is very simple. It's just the inverse of the number of classes, so of the number of counts. So if you have more counts, you give less weight. And then you have classes, the classes that have minority, very few examples, you give more weight. So, and then you define the weighted random sampler. So you have the sample weights here. So the number of samples, the ones that you do, and then you use replacement true. So which means that they can duplicate the data to make it balanced, especially for the classes where you have so much data. Yeah. So with this, we are ready. And now we can actually create, finally, the data sets that we want to use for the training. So we have the training data set, the validation data set, and the test data set. Yeah. So we use our function, our class, Retina dataset. The dataset that we already also calculated before. See, if we go a bit before, if you remember, we already split our database in training days and validation. So we'll use this as input now. The directory where we have the files, because now we are giving only the paths, if you remember. This will open on the fly. Yeah. So what is the advantage of this? This is also something that is worth mentioning. So there are two ways of doing this. So you can load all the data in your RAM memory, or you can do these generators as we are doing here. So where you only have the paths of the images, and then you read the images on the fly. So you read the image on the fly, you do the processing, like this cropping and pre-processing, and then pass it through the algorithm. Advantages and disadvantages. If you have everything in memory, so it's faster, but you need a lot of resources, especially for big data sets. If you have it from the disk and you read it from the disk, it's a bit slower. It depends a lot on the speed of the disk that you have. If you don't have an HDD disk, it could be a bit slower, but you don't need so much resources. So you don't load in the memory. Yeah. So you can choose what you need depending on your data set and depending on your resources. In this case, so we do it considering that we have limited resources, and then we can read it directly from the disks. Yeah. And the transformations are the ones that we do accordingly. Yeah. So we create the sampler. We create a dataset sampler for the training. Yeah. We only do this balance sampler for the training, but not for the test and not for the validation. Yeah. So meaning that we have to do we want to have a balanced data set for the training, but we want to evaluate in the real distribution of data in the test and also in the validation. So here we create a training with the data loader from PyTorch. So we give the training data set, we give the batch size that we want, and in this case, we use the sampler for the training. Yeah? So we use the sampler for the training, and in the case of the validation and the test, we don't use a sampler, but we have to set up the shuffle equals false. So this is also a good practice. So we don't shuffle the data every time that we do a training. So the validation and the test have to be not shuffle, always take the same, yeah? The same batches. Why won't you use shuffle in the data loaders? Because the sampler and shuffle are not compatible in the same. We either use a sample or a shuffle. So if you have data that is balanced, you can use a shuffle equal true for the training and not the sampler, yeah? So we are going to run this. So I don't remember if I run this, let's run everything. And now we are ready. So we have all the functions ready, and we want to plot a batch. So we want to see what kind of data we will use. So these functions will take basically a batch of images. It will extract with our data loader. We'll do the transformation just that we can visualize, and we plot the data to see how it will look, the actual data we'll use for the model, yeah? So we can run this, and we have this nice mosaic of images. So you have the first row with the training sample, the second row with validation, and third with the test. As you can see here, so now everything is in square, and also you see that with the normalization, the images look a bit more close together. So as you can see here, the images are exactly, there are of course differences, but you can see that also the contrast was increased because of using the CLAE algorithm for the pre-processing. As you could see that in the training set, even though we have a very unbalanced data set, the amount of images for each label is more or less similar. So it's not fully unbalanced. Yeah. If you see, for example, in the test, you see that from the 2, 4, 6, from the 8 images that we have 5 images, 6 images with label 0. This is because here there is not a balance, yeah? So this is the original distribution. So very important to use this balancing so that we have more or less even. Yeah. So with this, we are done with the data preparation. We have everything ready. As I said, this is a very important step. That is why I took quite some time for this, because it's the one of the most important things that we have to do for the test, for having good performance in the models. So now we are going to define the models. So we'll use some pre-training models and also some basic models. So I set up 2 very simple convolutional neural networks. We have, which are defined here. So we have very simple convolution layers, ReLU, max pooling, 2 of them. And then we have the final classifier with a flattened layer, linear ReLU, some dropout, and then a linear for the number of classes. And then that's it. One of the simplest convolutional layers that you can use. The second one is a bit more elaborated. So it has also batch normalization and max pooling. So to downsample the images. And then you have an adaptive average pooling in 2D. And the classifier is basically the same. Yeah. And we will use one family of pre-training models that ResNet. So ResNet is a very famous family of models, and there are many of them. So the first one was ResNet 18. So this is the lightest one. So we have a middle-sized one that is ResNet 50. And we have ResNet 152. That is a bit more heavy model. So these are the ones that we're going to train. And so we load the model. So the models come already with in PyTorch. So you can actually put just model, the name of the model. Yeah. And basically you have to do if you want to use pre-train or not. And you have to modify the final layer with the number of classes that you will use, because this is different for each one. Yeah. So here we define the models, and then we define a dictionary with the models that we want to train. In this case, we want to train 8 models. So the simple network from scratch. So I take the simple network class, I move to CUDA. The same for the other the other network from scratch. And what is important here is we take the pre-trained model, ResNet, from scratch. We set up pre-trained false, and if it's pre-trained, we set up pre-trained true. So we made a dictionary with all the models. If you want, you can, so here is comment, because the output is super big. If you want to see how the models look like, you can run this part. So that will give you a detail of how the models look. Yeah. And we go to the training part. That's the part that takes the most time. So I'm running this in advance so that you can see that I explain you the code, what is already training, so that we gain some time. So good practice here. So one of the main issues that you have always is that the model can overfit, right? So if we have too big model and too little data, it can overfit. So for this, we use a strategy called early stopping. So early stopping basically evaluates the data in the training and in the test. Yeah, in the training and in the validation, sorry. And if the model gets improving in the training, but not in the validation, it will stop the training. So that is called early stopping, a common strategy you see here. So the patience is a value like saying how much the validation will not we wait, because this is stochastic, right? So the validation could in one step not improve, but the next one improve again, and then we should not stop. But we what can also happen, what we decide here is like, we say if in 5 epochs the model doesn't improve for the validation, then we stop and we save the best model. So that is what this class is doing. And we define the loop. So when we are working with PyTorch, we have to define the loop explicitly. So meaning that we have to define the loop for the training, let's say by hand, in comparison if we use TensorFlow, for example. Yeah. So what we do, we define our device. There should be CUDA. The model, we move to the device, so it does everything in the calculation in GPU. What is the criteria that we use for this is the loss function? We use cross entropy loss. That is one of the most standard ones. For the optimizer, we use Adam with some learning rate that will give us input, and we have an early stopper. So we write everything in a summary with the summary writer from PyTorch, and then here we start with the iterations. So for every epoch, we basically calculate the training loss, and then we do a loop for all the images in the training. So basically here, we take the images in the batch, so for each batch. So we take the optimizer grad to 0, we have the criterion, we activate the back propagation. So we do one optimization step, and we increase the loss from the loss item. In the second step, we do the same for the validation, but in the validation, we don't train. That's why we have torch.no-grad. So it means that we are not training, we're just evaluating the model there. Yeah. And we save all the data here. And then we do a print with the evaluation and with the training and the validation loss. So you have the early stop. So if the early stop criteria is fulfilled, we stop the loop, and then we save the models. Yeah. So we save all the models, and then we return the model trained. So this is basically all what we need. And then we go basically to train the models. So actually what we wanted to do. Yeah. So we define a file, a folder that is called run all models, where we will save all the data. So we'll save with the data stamp so that we can track when it was trained. And then here we do the training for every model. So you can see for every model in our dictionary, we take the model that is already moved to CUDA. We have the log name. And we define the function, we train the model, the training loader, the validation loader. We use exactly the same for all of them. We have 100 epochs here. This you can reduce if you want to make it faster. And the learning rate, we use the standard one that is 1 for e at the -5 is 0.000001. Yeah, the smaller the learning rate, the slower it will converge, but probably more precise will be. So you have to always go into the trade-off. Yeah. So, but this is a good starting value. And then we'll see how the models are training. So we have the first model. So the simple convolutional neural network, you see in the first epoch, start with the training loss. It takes around 15 seconds to go in every epoch. And we saw that actually, with only 7 epochs, it is already done. So 7 epochs, and then early stop is triggered, model is safe. So we go to the second model. So in the second model, so we have the following. So we have already 13 epochs. So with the 13 epochs, you see that the model already stopped. Yeah. Sorry, with 15 epochs is still running, and then you can also check when there is no improvement. So no improvement, start the counting. 1, 2, 3. We have 3 already epochs that didn't improve. So it goes to the next step. If you have 5 steps, it will stop, like in the previous model. Yeah. So the training will take a few minutes, and I think I'm a bit close to the time. So I will let this run, and then we'll go to the next part of the code, that is the evaluation. So I will quickly go through the evaluation and then explain you, and then I will open the one that is already calculated so that we can see the results without having the train. But you see already that it's training here. So let me just quickly open the notebook that is already calculated so that we can have this, that we can see already the results, and I will guide you through them. Just 1 second, just only because of the time. Let me see where is open. So we will use Google Colab again just to open this so I can show you. And then I will upload my files, quickly the one that is already compiled, so that we can see it. Sorry, it's uploading. Just 1 second, and then just of time. So in the background, is still doing the calculations. So you can run the calculation. It will take probably 10 to 15 minutes to run all the calculations. But we wanted to go to the analysis of the data. Yeah. So and now we evaluate this. Important. So you don't evaluate in the validation test, but on the test that is fully independent, right? So please be sure that that you evaluate in the test, not in the validation. So this function will do three things actually. So since we have a multi-class model, so one way to evaluate this is through the confusion matrices. That's basically a matrix that is giving you how many items were classified properly for each class. Yeah, and also from the ROC curves. Yeah, so basically what you do here is you open your test set, you do the predictions, and then you can also calculate the score of the predictions. So you generate the confusion matrices. So you also have a report with accuracy, precision, and so on. Then, since you have a multi-class problem, so we have to binarize this. So meaning we have to split the problem in binary for each one if we want to calculate the ROC curves and the AUC. So this is what is done here. So it splits for any of them. They calculate the scores. It will print the score so you can see, and it will plot the curves for each of the class. Yeah. So this is the function, and then we have the loop to do it for all the models that are trained. So basically here you take the folder where you have your models, we'll open the models, and we'll do the evaluation. Yeah. So I'm sorry, I think for some reason I cannot see it. So it has not run. Sí, yes. I said recompile. Yeah. Yeah, perfect. Thank you. Yes, this will be better because they have the problem with the compilation now. Just give me a second. I will check it and then yeah. 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 It's here, right? Yeah. Exactly. Yeah, perfect. Thanks a lot. And that is me. Wait. Yeah. Thank you. Yeah. So now I will go use the compile version. Yeah. Thanks, Rashid. So we have all the trained models. So we evaluate, and then we will have an output like this. So you have a report where you have the classification, all the precision, recall, F-score, and the support, meaning how many images were evaluated. And then you have also the accuracy. And what is interesting is the confusion matrix. So you can see here in the simple model, everything was classified at grade 0. So it's a very bad model. And then something that you can see also in the ROC curves, all of them are in the diagonal. So meaning that basically the model is doing some random selection. Yeah, very quite a bad model. So we got a model more elaborated, the simple one, the simple convolutional neural network by Scratch. So you see that the accuracy is a bit better, 30%. Also the confusion matrix. So this is a normalized confusion matrix. In an ideal model, everything should be 1 in the diagonal and 0 everywhere else. You see that some classes got a bit better. So for grade 0, so 41% was already properly classified. For grade 1, 39. Grade 2, that didn't work. And grade 3 was quite bad. So you see that the curves already start deviating a bit for all the classes. So meaning that the model is getting better, but still quite bad, no? So our AUC is around 0.5, 0.6, which is actually a bad model. So we have to aim to values of 1. That would be ideal model, but more than 0.8 would be really a good model. And then we start with the pre-trained models. So with the standard models, with ResNet from scratch, we see that 2 classes are good, the rest are not so good. So the curves start getting better. But when we use a pre-trained model already, so we use the weights that we had already from ResNet, we see that it starts getting much better. So you have 50% classification for 2 classes. The third class is even 75%. And the second class is still a bit problematic. And then you also see how the ROC curves get much nicer. For example, for class 0, you see already that you have 0.8 AUC, and for grade 3, you have 0.88. So these are the curves that you see here, and then it starts looking quite much better. So ResNet with Scratch, also not so good. It failed. It tends to classify everything as grade 2, but also not so good when we have with the pre-trained model. Yeah, so which means that using a bigger model not always means getting better results. You see, for example, if you have to choose between ResNet 18 and 50, 18, even though it's a smaller model, gives better results for your data set. So, and then we go for ResNet 152. And then here we see a better improvement. So you see the 2 classes, 0 and 3 are better. Second is quite good. 1 is not so great. So the ROC curves are also better. So you see the ACU values are quite good for grade 0 and 1, and relatively not so great for 1 and 2. And if we use the pre-trained model, here we see similar results, yeah? So what we can conclude from here is that actually the larger model, ResNet 152, was the best, and it behaved more or less the same from scratch or pre-trained. So Retina 50 didn't work. So as I said, this is also a little exercise. So we are not looking for a perfect model here. So there are still many things that can be tuned. So the pre-processing can be improved. The times of the learning rate can be adjusted, for example, to make it slower. So there is still a big room for improvement, but the idea here was more or less to show how we can set up, how we can choose the models. So then we get the best model by using the AUC rock macro. And here you have all the values for all of them. So this is the macro, this is the average, the average AUC. And then you see that the best model was Retina from scratch that gave the largest AUC. Yeah. So this is a very this is the simplest way to find the best model. So you can also do a deeper analysis, for example, with the confusion of matrices and so on. And in the final part, in the last minutes, I will talk about the class activation maps. The class activation maps are actually a way to visualize if you want to put it in simple words, what the algorithm, what the model is seeing to classify. It means it gives you a heat map of the image, of the regions of the image that are the most important for the classification task in the last layer of the model. So we take the last layer of the model, and we see which part is all the attention of the model set, or gives more important to which regions are more important for the classifications, and we plot it. And this will give us an idea of if the model is working properly or just taking random stuff for the classification, and also try to understand if this is physiologically relevant. So here we have the function. I will not go through it, but it's basically what I summarized. And then we'll take 5 examples to plot. So here we have a loop that will take the 3 top models. So you can also do it for all of them. So, but here I take only 3 of them, the 3 top models, and we'll do the class activation maps. And here I show you an example of how it looks. So these are the best models, and these are the regions that we're taking for the classification. So you see for grade 0, for example, the best model focus the attention in the macula, where it's basically probably showing that the retina is healthy. Here, for example, when the predicted when there is a failure, you see that it's focusing in the same region, so the algorithm failed in the region where it has to be focused. Here's another example where the algorithm also failed, and then you see that basically took the whole retina to the classification, which is not so good. But if, for example, if you see the pre-trained in the second model where it did actually good, so it focused more or less in the same region. Yeah. So what are the idea of these CAMs, the class activation maps, is that you could try to understand a bit more what the algorithm is doing, and this will also help if you go to real world applications. So probably a clinician will not blindly trust the algorithm because it can have errors, as you have seen. But if you have the classification plus the algorithm tell you, okay, I'm classifying this because I think this part of because according to the model, this part of the region is important for the classification, the clinician could go double check and ensure that actually what the algorithm does is properly. So this gives not only the black box that we have for classifying, but also some interpretability. Yeah. So with this, I finish. I just wanted to go to some challenge and limitations. So we saw that we have unbalanced data. So here I put one of the solutions, maybe not ideal. So if you want to continue this, I will encourage you to try other options of balancing the data. So we have overfitting with small data sets. We still have a relatively small data sets for this kind of models. So you could see that the early stopping was done quite quickly. So obviously increasing the data will be the best. Yeah, so be careful with the input size. So this will already check. Be careful with the CUDA errors. Yeah, so try to check. You have the one step to check where they have problems. Yeah, And also be sure that all the networks in the counts, there can be failures. So now this test, but if you have another model, be sure that you check the proper layer from where you want to extract the data. Yeah, some things that could fail, especially if you add more models in this case. So some technical and clinical limitations. So of course, the data is biased. It's from some labs in France. So probably if we try this in people in South America, for example, it's likely that it will not work, even if the model is quite good, because the data sets are limited and biased. So the label quality is something that has to be checked. So this is already a setup that is very well established, so we don't have many issues with this. And so we have a lack of explainability. So we try to do it a bit with the counts, but still it's a black box. So with this, I want to thank you again, and I want to finish the presentation. And now I will be open for questions, right?
Exactly. So thank you, Anna, for this great tutorial. And I think I will start with the question. And if the audience do have questions, please either like raise your hand or write them down in the comment section. So I will start with two questions. The first one is, can you explain a bit about like the impact of image resolution? So like we are working with like sometimes big images, and where should we like be caring about the image resolution? Because like you mentioned at the beginning, for early grades, it's very difficult to see actual lesions in the images. So should I always downsample the images, or should I do a trade-off and think more?
Yeah, I think that is a great question. So for these models, we also have so we have to think about a trade-off between the resources that we need and the resolution that we have. So this is one thing, because we cannot put images with super high resolution in the models because it will not fit in any memory. So unfortunately. But the problem with the downsampling going low in resolution is that you can also miss details that could be important for the data. So in general, I think the general suggestion in this case is to check and then go in a trade-off of how much resolution I can go and still get good results, and then not lose information that could be relevant. Yeah. There have been a couple of papers showing in classification and also in other tasks like segmentation in images, that having the highest resolution is actually not the best for the models. So that in many of the models, they actually behave better when they have better context and lower resolution. So this is very problem dependent and depends a lot of the characteristic of the data and the details that you want to see. So one suggestion, if, for example, you understand that you know from the program that small details with high resolution are the ones that are important for the classifications, and still want to pass this to the models, so you can use, for example, patching, means cutting the image in small patches and then analyze by patch, and then have a classification of the whole image in high resolution. If this is the case, it's computationally more expensive, more complicated, but if the importance in the specific problems are the details are coming from small details in the images or small regions, that could be a useful approach. But it's always a trade-off,
Yeah, okay.
the solution.
Okay, thanks for this detailed answer. Since we have question from the audience, I think we will take it by order. So Carlos asked, I would like to ask how suitable, optimal it is to use convolutional autoencoder for this type of classification task.
Yeah, cool. Thanks, Carlos, for the question. That is a great question. So we talk here about only supervised learning. So we have the label, we have the images and the specific label, and that's why we use these kind of algorithms. If we use autoencoders, so the autoencoders basically what they do is get a latent space that get the most valuable information of the images. And this is a very cool data, because with this you can even go one step further and use, for example, unsupervised methods to see to do classifications. Yeah, so meaning that in principle you don't need model, you don't need labels, but we can use this data to use, for example, abnormality detections. Is one of the most common examples, right? So you see, you train only normal data and then see things that only deviate from the normal. The disadvantage is that you will not have a grading, but you can just look for abnormalities. Is one option, or you can use clustering techniques on the latent space, and then see if you can identify different clusters of data, which in this case will belong to different grades of the disease or normal disease, and it's also a valuable approach. But it's a different approach from the one that we tried today, that it was a fully supervised one.
Okay, thanks for the answering. And next question is from Shatuna. She want to ask about, can you give us more detail about data imbalance and how to handle data imbalance, like you mentioned during your presentation?
Yes. So yeah, that's an interesting question as well. So I mentioned in the beginning very briefly that there are several strategies to deal with data imbalance. So for this tutorial, we choose one specific one that it was just taking the trying to balance during the training in the batches. So this is one strategy. Other ones that one can use or can even be combined is, for example, we can generate artificial data to balance the data. For example, the simplest one would be just duplicate the data, the original data for the minority classes, so that we have more or less the same number. One option. Other option will be to work in the when we do the augmentations, do more augmentations, for example, in the data that is in minority. So do, for example, few augmentations in the data we have a lot of, in the classes we have a lot of data, and do more augmentations in the data that we have fewer representatives. Another option is also to include this in the loss function, so to give more some penalty to the, so different weights when there are errors in the classes with a lot of data and classes with less data. So these are different strategies. This also can be combined. Probably, if you combine many of them, you will get the best results. But also, this comes with the problem that you will need more resources, of course, to do all these operations. That's something that you could try.
Okay, thanks. Perfect. I think Ayub had a question, so maybe you can unmute yourself and ask.
Yes, thank you for your presentation. It was very informative. My case, I'm trying to build a binary classification model to classify images into two classes, diseased or normal. For the diseased class, I'm trying to combine multiple diseases like DME, DR, glaucoma, and cataract, and put them in one class. And the second class is just normal images. And when I'm trying to train the model on this data set, the problem is that I get very poor performance, and then I'm not sure what is the problem exactly. Maybe it's related to the to each disease area of effect. So each disease affect a specific area. So maybe this is the problem. So I can't find why I get this poor performance. Also, I have tried to use many techniques like data augmentation to augment my data and so on, or also cross validation, but I still get the same problem. So any suggestion is possible.
Cool. Thanks for the question. This is a very common problem usually when we start. So of course this depends a lot on the specific characteristics of your data set. But from what I understand, probably the main issue comes from the variability that you have in the different diseases that you have in your one data set. So what I will highly recommend for this before going to the models is try to do an exploratory analysis of your data, the data that you have. So meaning, For example, you can try to take the images that you have in the control and the different diseases, and then see how variable are in terms of intensity, contrast, and brightness, for example, or things of position, or if it's only like the changes in the disease are specific parts. So that will help you to understand what kind of techniques you could use to improve the data, because maybe it could be that the variability is coming from just variability in the way the images were acquired, and this usually can be fixed or improved doing some pre-processing in the images, like some normalization of the intensities, some adjusting of the contrast, if this is the problem. So if not, so you can go a bit further, and then maybe you can try to split not in one single group of normal plus diseases, but maybe try to group the diseases in two classes, so you have multi-class problem, and maybe the algorithm will be better trying to distinguish this from the normal. This could be a possibility, but it depends a lot on your data set. So I would recommend you first to do an analysis of the data that you have, and also see if you have enough data to run this kind of algorithms, because this also sometimes the bottleneck, right? So that you don't have enough data. And so if you don't have enough data, even if you use a lot of augmentation techniques and so on, it would be complicated to get good performance.
Okay, thank you.
Okay, so we will also take the question from the chat, and then I will be giving the place to Abdelak. So the question from the chat was, are there any other analysis tool that got come? I heard about like shape and line analysis. So maybe you can introduce them if you know them, and yeah.
Okay, this is a great question. So as I said, so the grad, so the class activation maps is like the simplest one method that we have, and actually nowadays there are more implementations of and more advanced implementations of the class activation maps. So the one that I showed here, it was the simplest one. It was just to give you a hint, a taste of what you can do with this kind of interpretability. And so also the disadvantage of the class is that you also visually will start judging, and it depends on every image. But there are a lot of methods that can be done. So one of the most common one is or most popular one is the one that you exactly mentioned, is the SHAP. So this is the Shapley adaptative explanations. So this, I think, probably one of the most popular to explain the output of the models, because it provides local explanation based on in the game theory. So this is probably, if you have to go like for more real world experiments, is one of the approach to go. So I would go probably for, so you already mentioned the GradCam. So the GradCam, it was exactly one of the most advanced models of the class activation maps. So these are two of the most popular approaches, and then two of the one I would suggest to go also if you want to have more interpretable models in this sense.
Okay, thanks for the answer. We will go now with Abdelak. You can like unmute yourself and ask your question.
Thank you, Rashid. Thank you so much, Andre, for the notebook and the presentation. It was very insightful for me, and I learned a lot. I have two questions. The first one regarding the data imbalance. So you mentioned some techniques for data imbalance, and you mentioned also a technique which is weighting the loss, I think. So how we could do that? And the second one is regarding the transformations that we can do on this kind of images. You mentioned that there are some transformations that are physiologically acceptable. I don't know when I can find this kind of information in the case of this retinal images, for example. Thank you.
Okay, cool. Thanks for the questions. So they're very, very important. So I will start for the second one, for the augmentation, and then we go to the imbalance. Yeah, for the which augmentations to use and which not to use. So for this, it depends a lot in the problem that you are working on. For example, you have X-ray from chest. It's not this, you cannot apply the same images, X-ray images from the chest, for example. You cannot apply the same data augmentation if you are using Retina. Because how to get what you can do. So you have to go a bit into the literature of the specific problem. So in the Retina, the ones that I mentioned are the most commonly used, and more or less I explain you why some cannot be, because like you cannot flip vertical flips in the Retina, right? Because it will mean that the person is upside down when it was taking the image, so it's not physiologically relevant. But the Retina can be symmetric. There's something that can be also checked in the literature, and also the rotations. So in the Retina is a very symmetric system, right? You have basically a circle, and the circle can be rotated, so you don't have so rotations can be introduced also from the tilting of the image when the image is taken. So it's something that can be used, but also you have to think like if you have a small rotation, it's not the same that you have like 90 degrees rotation. So 90 degrees rotation will not be valid for this problem, which because also will mean like the camera flip 90 degrees, which is not really possible. So in this case, I will recommend for the specific problems to check a bit of the literature and check how first understand the problem exactly. So in the Retina, I told you like some explanations of why some things can be done and other things cannot be done. So many of them come from the way the images were taken, and many of them from the actual structure of the image that of the object that we want to analyze. So we have to be careful and check the literature first about the system, and second the literature about what was the specific microscopy technique that was used. So because also like variation in contrast and for contrast and brightness can be common from using different cameras, different microscopes. Yeah, but they also should be mild. So you cannot put like high values there as well. So you have to be very careful. And there are also, for example, you can have elastic deformations, and elastic deformations are the ones that you have to be the most careful because this can change actually the shape of the object that we want to analyze. So these are mostly not recommended for most of the cases in medical imaging, but so the general suggestions will be to go through the literature, understand what is the physiology of the object that we want to analyze, in this case retina or chest or whatever. Understand also the imaging, how the imaging was done, so and the imaging technique, and then based on that decide what kind of transformations to do it. If you are not sure about something, it's better not to do it, yeah, because it can introduce artifacts and it can make the model to give stuff that is not relevant for this, yeah. So this in the general, yeah. So for the second question, for the first question about the lost with weights. So if we are using PyTorch, when you define the cross entropy function, if you remember in the loss function, you can put a flag with the weights. So there is also simply you can use a flag that is called weights, and then you put the weight similar to the one that we use for the batch. And this internally does the compensation for the imbalanced data. So this is one option, or you can use other functions for the classification. For example, you have a binary problem. So there is one that is called PCE with logistic loss. So, but this is specific for binary classification. So this is one where you can also do a binary classification with loss function. Or so this will be the two. But so the easiest will be just to put the flag with the weights in the cross entropy loss function that you have in the code. So it's just one flag, and you can use the same weights that we use to do the sampler.
Thank you so much. Thank you.
Okay, thanks for answering. And we will be going through the last question in the chat that is coming from Ejibulai. I think I hope I pronounce well. So it is okay to use cross entropy loss with two output neurons for binary classification. He said that he gets errors whenever I try to use binary cross entropy loss with a single output neuron. So what should be the the good way to do it with his problem when using the loss?
Okay, so if I understand correctly, so the cross entropy in general should not be a problem and should work for binary classification, even if you have to with the two outputs in the binary classification. I should not be a problem. I don't know why it could be if you use a single output. Sorry, this I don't know what could be the problem. Sorry. So we have to have a look. But in general, the cross entropy should not be problematic when you use binary classification.
Okay, so is anyone have another question that they want to ask? Don't be shy. There is like still left some minutes to ask questions about the about classification problem in deep learning, on specifically what was tackled in the tutorial. So I will ask a question. In fact, I will ask my second question now, and the question is about so let's say you are training your model, and then you are saving checkpoints. And what is usually the best way to save checkpoints? Should I save checkpoints at every iteration? Should I save checkpoints like when the losses decrease, when the IEC increase? What is, according to your experiment, the best way to save checkpoints?
Okay, that's a great question. So of course you can always save in every epoch and then have all the information. But so in my experience, or in the practice that we have had, I think the best policy to do so is to say when you have an increase a decrease in the loss function, meaning when the model improves. So because basically you are saving the best model checkpoints. So that would be my suggestion.
Okay, yeah, thanks. Thanks for the. So we have another question from David, and the question is about black pixel. So since the black pixel are zero, or will it affect the competition since convolution won't be affected, right? Please clarify.
Yes, so indeed it will. I mean, if you have the full convolution in the full region with zeros, it will not do anything. Yeah, that is totally correct. So the removing of this black space is more like into getting more information of the image, because you have a lot of black space. So when you do the input to the image, so basically you have a limited resolution that you can put as an input, right? So if you have a lot of black space, we are giving also information that is not useful for the algorithm. It's more than in that sense, not that we get artifacts from the convolution itself. So you have a lot of black space, you have a lot of information that is not useful for the classification. And since you have to resize, you can lose information also in the resolution, right? So the idea of removing all the black space is that you have really only the region of interest of what you want to analyze and give a clean data to the algorithm. Try to remove as much as possible of the information that is not useful, but not really with because you are right. So in the computations it will not affect because we have just past zeros, but you are giving basically useless information to the algorithm. So the idea is just to give information that can be used for the classification that is relevant. It's got more in that sense about the 0 pixels.
Okay, thanks again for answering the question. So maybe I will answer the question from Carlos. So thank you for the great talk. Maybe could you provide us more information about MICAI? So MICAI basically is it's first a society and also a conference that is basically tackling medical imaging problems in the deep learning area. So it's medical imaging analysis, and today is more centered around deep learning, and it's do have a lot of workshops. So the conference is active every year, and there is like the main track and some small track with workshops that are tackling very niche stuff. For example, we have workshops on ophthalmic data, on MRI, and for example on longitudinal data. So you can find any type of problematic that you are working with medical imaging in MICAI, and it's typically they typically each year provide like the state of the art solutions about a defined problem in medical imaging. And if you want to have more details, you can go in this link, and also I will be adding details in this page about like Rise Mikai and Mikai. So yeah, please feel free to go there. And I think for the question we are done. If there is no one else, so there is
That's right.
is there this is there is a from David, is there a data set with image as well as clinical data as a CSV file, or do we incorporate both text and data for image for a model? So I will let you answer this question, Anand.
Yeah. Yes. Thanks. So let me see if I understood correctly. So in this case, you want to have a model that not only a convolutional neural network, but also a model that takes information about some clinical data that can be, I don't know, could be anything related. So it is possible to do. So in this case, you have to work with models that take multiple inputs, and there are also several ways how to implement this. So on one side, you will have the input for your neural network that will, at the end, the neural network will produce one vector, right? So you can have a second model that will take all the text information that should be, of course, processed and then made it numerical so that you can also process with some other model. It can be another neural network, and then you can combine these two results to make the final decision of the classification. This is one strategy. So you have this multimodal input. So this would be the simplest way to do it, right? So you have multimodal multimodal inputs at the end. You have some text with the clinical, and then you incorporate this. So this will be one option. So you somehow have to first change the data, the clinical data to numerical data. So to categorize, or depending on what data you are talking about, so you can also either go through another neural net, for example, to the classification, and then just combine the last two layers of the two models and make the final classification, or you can put directly to the model. So some strategies. There are, of course, more elaborated strategies nowadays, but this is more or less the general idea. But this is totally possible.
Okay, perfect. Thanks again. I think we are done with the questions. So maybe the last question that we can take. We are almost 2 hours into the tutorial.
Okay.
So last question from Shintuna. That will be the last. So,
Yeah.
sir, if we apply edge detection in the pre-processing, can it help increasing the model accuracy?
Yeah, yes and no. It depends on the problem. Yeah. So of course, technically, the neural networks also act as edge detectors inside, right? So when they calculate, all the convolutions and detect probably potentially the edges that you want to identify that are relevant for the classifications. If your problem is really focused on specific characteristics related with edges, it might be that that improves the classification if you use this in the pre-processing, but it can also be that when you do so, you remove details that can be important for the classification. So you have to be very careful with this. So, because anyway, the neural network is identifying edges inside somehow. Yeah. So edge detection is something that maybe is not particularly suggested to do this as a pre-processing and give this as an input for the network.
Okay, okay. Thanks again for answering. And so I will close now the tutorial session. So once again, thank you a lot, Anand, for this clear and dense tutorial. And it was very interesting. Very liked it. And also thank the audience for being here. And so this tutorial was recorded and will be available on the Mikai YouTube channel later on. So I will be sending you emails to notify you when this is done. And as we presented, this tutorial is available on the Rise Mikai tutorial website using this link that I will just redrop in the comment section. And finally, we will come back to you with the dataset issue. It's probably like a
The
right.
permissions
Yeah,
are,
permission
yes,
and yeah.
the
So yeah,
permissions should be problem. Yeah, so I will fix it now.
yeah, yeah. So that's perfect. And so thanks you again, and see you guys another time. So bye bye.
Bye. Thanks again. Bye.
Bye bye, everyone.